Another useful operation you can do on vectors is called the cross product. So what that is it's written as A cross, so an X, B, and what it outputs is another vector, vector, I'll call it C, that is perpendicular, I spelled that right, to A and B. All right, so we've got two vectors, so let's say vector B here and vector A. Let me draw it a little different. A. Then I want a vector that's perpendicular. That'll be the output of A cross B. All right, so since these vectors A and B are both lying in the board, there's only one place it can go. It's either directly out of the board or it's directly into the board. Those are going to be both perpendicular. All right, in general though, you can also, now that's in 2 dimensions on the board, but in 3 dimensions, you take two vectors, A cross B, then you've got, a vector that's perpendicular like that, or it could be this long, or it could go the opposite direction, or, any length, so there's still some ambiguity about what it should, the length should be and which direction it should go. Essentially, we're going to choose an A cross B, a vector that's perpendicular that's convenient for us. And here's how we're going to do it. So first off, I just want to write, vector A is made of A1, A2, A3, and vector B is B1, B2, B3, and then C, similarly, is C1, C2, C3. All right. So vector C is perpendicular to both vector A and vector B. Then we should have A dot B equals 0. A dot C equals 0. We should also have B dot C is equal to 0. Because one of the properties of the dot product is when two vectors are orthogonal, they're right angles to each other, then their dot product is 0. But then if we write that out, that's the same thing as, dot product, it's going to be A1, C1 plus A2, C2 plus A3, C3. And then for B, it's B1, C1 plus B2, C2 plus B3, C3. And just to emphasize, right, those have to both be 0. So we're going to try and pick a C1, C2, C3 that satisfies both those equations. And it's a little algebraically intensive, so I've got notes. So the first thing we're going to do is we want to eliminate C3. And one way we can do that is we're going to multiply the top equation by B3. All right, so I'm going to write this as B3 multiplying A1, C1 plus A2, C2 plus A3, C3 equals 0. The whole equation. And then I've got A3, I'm going to multiply B1, C1 plus B2, C2 plus B3, C3 equals 0. And then I'm going to subtract them. All right. So the way that's going to get rid of the C3 component is I end up with B3 times A3 times C3. And here I end up with negative A3 times B3 times C3. Add them together, they cancel out. And 0 times B3, 0 times A3, still 0, so 0 minus 0 is 0. But then if we write this out, so I've got A1, B3, so I'm going to group these by C. All right, so I have A1 times B3 minus B1 times A3. And what else do we have here? All right, we have A2 times B3 minus A3 times B2. And then 0 C3, we wanted that to happen. And now the next thing we can do is, okay, well, if I want to pick C1 and C2 just to get this whole equation equal to 0, we can pick C1 and C2. All right, going back to my notes. So we're going to pick C1 is this piece right here, this A2, B3, yeah, A2, B3 minus A3, B2. And so then we'll end up with C1. So we have A2, B3, so this piece times that piece. Then we're going to set C2 equal to negative that piece. So negative A1, B3 minus B1, A3, which is equal to, okay, I get to reverse those now, B1, A3 minus A1, B3. Right, if we do that, then we kind of get one thing and then we're adding a negative version of it and they both cancel. So that's one way to do it. So we've got a candidate for C1 and a candidate for C2. Fortunately, we don't have C3 yet, so let's go ahead and do that. Okay, but we do have two equations. So we are going to reuse this equation to try and solve for C3. So we've got A1 times C1 using the top equation. We've picked C1 to be A2B3 minus A3B2. A2B3 minus A3B2. So that was my A1 times C1. And I have plus A2 times C2. We picked C2 to be B1A3 minus A1B1. Sorry, I messed up. I meant to keep everything alphabetical. So here we go, A3, B1 minus A1, B3. And then we have our plus A3, C3. Oh man, all right. So now we got to solve for C3. Well, now we get to multiply everything. So we get A1, A2, B3 minus A1, A3, B2 plus A2, A3, B1, yeah, minus A1, A2, B3 plus A3, C3 equals 0. Okay, what can we cancel here? Okay, A1, A2, B3, A1, A2, B3. Okay, perfect. We can cancel that one with that one. And then we can actually divide out an A3 everywhere. So we end up with negative A1, A3. No, sorry, A1, B2. A1, B2. Right from here, I divide out the A3 and have plus A2, B1 plus C3 equals 0 if I divide out A3. And so then that would mean C3 is equal to, okay, just negate this. So it's A1, B2 plus A2, B1. All right. So now, if I write it out somewhere, I'm going to have to erase. If I write this out, it ends up being, all right, so A2B3 minus A3B2 that was the C1 we had picked, and then for C2 we've got A3B1 minus A1B3 sorry, A1B3 A1B3, yeah, comma, and C3 is A1B2, excuse me, minus A2B1. Okay, and just double checking here. A2B3 minus A3B2, A3B1 minus A1B3, A1B2 minus A2B. Okay. So, this is the vector that's perpendicular to both A and B if I have the components of A and B, you know, A1, A2, A3, B1, B2, B3. But again, we kind of arbitrarily choose C1, C2, C3 when we could multiply these all by some constant, you know, by 4 or negative square root of 2, whatever. It would still be perpendicular. It turns out this is the definition of the cross product, and it has some really nice properties it goes with, kind of like the dot product did. So on the next board, we'll go through what those properties are. So here's the cross product, and this is the definition here. And the first thing you're probably wondering is, how am I supposed to remember that, right? It looks like a pretty bad formula, and where the 2's and the 3's go, it looks bad, right? Turns out there's a nice pictorial way to remember it, so go ahead and do that. So I have A cross B equals, so I'm going to draw this. It's the determinant of a 3 by 3. If you don't know what a determinant is, there's a nice pictorial way here. So remember vectors I and J and K, right? So those were in the x direction, length 1, y direction, length 1, z direction, length 1. So those are going to be nice for this pictorial way to represent it. In the second row, I'm going to have A1, A2, A3. And the second row is A because A is the first argument here, right? It's A cross B. It's not B cross A. In the bottom row, we're going to have B1, B2, B3. Right, and so when we do this, we're going to have I vector. So here we go. We're going to draw a bunch of diagonal lines. So we're going to have I times A2 times B3. And I'm going to draw out the rest of this just so I have room. Okay, and then J. It's a curse of J. Okay, I think that'll be enough room. All right, plus K. Okay. All right, so I'm going to have I times A2 times B3, but then I'm going to have same diagonal, you know, going this way. I'm going to have J times A3. I kind of have to come backwards here, and then B1. So J times A3 times B1. J times A3 times B1. All right. Then I'm going to have K times A1 B2. So that's only half of it, though. So the other half is I'm going to draw another one for convenience here. So just a sec. I, J, K, K1, A2, A3, B1, B2, B3. You could probably do this in your head after a while, but it's a little busy if I draw all of them at once. Next, I'm going to have I, and I'm going to go the other direction. So I'm going to have I times A3 times B2, and I'm going to have minus. So it's negative I times A3 times B2. All right. Then I'm going to do the same for J. I'm going to have J times A1 times B3. Sorry, negative J times A1 times B3. Then same thing for K. I'm going to have negative K times A2 times B1. And as you can see, that matches. So here we have A2, B3 minus A3, B2, and that's in the x components, and I is, you know, the vector pointing in the x direction. Then we have A3, B1 minus A1, B3 for the j component, and then we have A1, B2 minus A2, B1 in the k component. So this is a very nice pictorial way to remember what the cross product is, how to calculate it. All right. So with that, let's just do a couple examples first. All right, so first off, we got this nice pictorial way to remember it. It's related to determinants somehow, maybe. And so let's cross a couple things. So what if I cross 1, 0, 0, cross 0, 1, 0. All right, so in 3D space, I gotta be careful here. All right, so that's x, y, z, and so I've got a vector going that way. I've got a vector going that way. I'm crossing them, and I'm crossing this one to that one. So the one on the x-axis cross the one on the y-axis. What will that end up equaling All right, well, let's go through here. So, yeah, let's just have to do it. All right, so we have A2 is 0, so that's gone, right? It's going to be A2 times B3. A2 and B3 are both 0. We have A3 and B2. Well, A3 is 0, B2 was 1, but 0 times 1 is 0, so the first component's 0. Next we have A3 times B1, so A3 is 1, but B1 is 0, so that's nothing. Then we have minus A1, sorry, I mixed that up. Sorry, A3 times B1, that's 0 times 0, minus A1 times B3, that's 1 times 0, so we get 0 minus 0, we get 0. And then next we have A1, B2, so this is A1, this is B2. Okay, so I have 1 times 1, it's 1. Then I have minus A2 times B1, minus 0. So it ends up being 0, 0, 1. And so the cross product ends up going that way. All right, so one thing hard to see on the chalkboard, but I can go ahead and do it down here. This right-hand rule is, this cross product is following the right-hand rule. So if I have two vectors and I cross, let's say the purple one to the yellow one, so purple cross yellow, the longer one cross the shorter here. I'm going to start at the purple, going to curl my fingers towards yellow, and this is the direction that the vector comes out. So in here, I got to contort myself a little. So if I have x, this vector here, 1, 0, 0, cross this vector here, 0, 1, 0, and I curl, it ends up going up. So this cross product, it follows the right-hand rule. So it uses right-hand rule. That's going to mean that if I had crossed 0, 1, 0 with 1, 0, 0, meaning the opposite direction of these two, that'll actually end up being 0, 0, negative 1. It ends up going the opposite direction. So that's a little weird to do it that way, but so if I were to go from, let me draw it on the board. If I were to have x, y, and then z is going this way, positive z, I have one vector there, one vector there. If I do 1, 0, 0 cross 0, 1, 0, then right-hand rule, I'm going in the positive z direction. But if I were to cross 0, 1, 0, so the upward one, cross 1, 0, 0, so I'd go like this, then my thumb is going to point into the board. It's going to be the negative z direction. So it follows the right-hand rule. Well, that's nice. All right, so we know that the cross product is, forms a right angle, a vector that's perpendicular to, A and B, pops out a new vector. We know it follows the right-hand rule, so we know which way it points, so that ambiguity's gone. The last one is, okay, well, what is its length? And geometrically also, what does its length mean? So I had to do this board beforehand. I didn't write it as I went because it was really complicated. So let's go ahead and go through. So if you want, the answer at the end of this is the magnitude of A across the magnitude of B equals magnitude A times magnitude B times sine of theta, which theta is the angle between the two. If I have A, B, that's theta. All right, so that's the answer. If you want to skip this then on how you get that relationship, you just go to the next board, skip the video. But if you care, let's keep going. So in order to get this relationship, we're going to start with A cross B magnitude squared. All right, so I've got the three components of A cross B, so A2B3 minus A3B2. I'm squaring it because I'm computing the magnitude, plus A3B1 minus A1B3 squared plus A1B2 minus A2B1 squared. Then I squared the magnitude, so that square root, that's normally on the magnitude, I squared it, it's gone, so it's just the squares of each of the components. All right, so next up, I multiplied it out. So if you multiply this piece out, you'll end up with these three terms, right? So a2 squared, b3 squared, you get a3 squared, b2 squared, and then in the middle, since it's minus, you get minus 2, a2, a3, b2, b3. Same thing for the next one. So we end up with a3 squared, b1 squared. In the end here, we get a1 squared, b3 squared. In the middle, that's minus, we get minus 2, a1, a3, b1, b3. Last one's the same. All right, a1 squared, b2 squared, a2 squared, b1 squared. In the middle, we get a1, a2, b1, b2, and then minus 2 of that. All right, so now we have a horrible mess. It's going to get worse before it gets better. So this row here, multiplied out, the magnitude of the cross product squared. And then this piece, I've split this row here, this equation, into two pieces. So one piece is on the top here, one piece is on the bottom, the minus 2 stuff. So here I have this a1 squared, b2 squared, that is right there, right? I have a1 squared, b3 squared, a1 squared, there, b3 squared, and there it is. I've got a2 squared, b1 squared, that is, there it is, a2 squared, b1 squared. I've got a2 squared, b3 squared, and there it is. Got a3 squared, b1 squared. Where is that? There it is. Then I've got plus a3 squared, b2 squared, and there's that one. All right, so those terms were all there. So I got, that one, and 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 that one. But then I also have my minus 2 stuff. So I've copied those on the bottom. All right. Then in the middle two, I've added terms, but I also subtracted them, so I didn't change the equation. So if I add a1 squared, b1 squared, and I also subtract a1 squared, b1 squared, then it's the same equation. All right, and I've done that a few times here. Also a2 squared, b2 squared, and also a3 squared, b3 squared. Well, why did I do that? Well, it turns out if you take the top two rows now, that actually all comes together to be a1 squared plus a2 squared plus a3 squared quantity times b1 squared plus b2 squared plus b3 squared quantity. Right, so I have a1 squared b1 squared, I've got a1 squared b2 squared, I've got a1 squared b3 squared, I've got a2 squared b1 squared, I've got a2 squared b2 squared, I've got a2 squared b3 squared, I've got a3 squared b1 squared, a3 squared b2 squared, and a3 squared b3 squared. So I was able to take the top two rows, put it into this. Okay. Then next, I took the bottom two rows, and I was able to put that into this. So if I can do the squares, that's nice. So it's a minus, so I have a1 squared b1 squared. Well, there's minus a1 squared b1 squared. And I've got minus a2 squared b2 squared. Well, there's minus a2 squared b2 squared. And I've got minus a3 squared b3 squared. There's the minus a3 squared b3 squared. Then because you're multiplying these across each other, we get a1 b1 times a2 b2 twice, so minus 2 a1 a2 b1 b2. We also have a1 b1 times a3 b3 twice, so you have minus a1 a3 b1 b3, a1 a3 b1 b3, minus 2. And you also get a2 b2 minus a3 b3 twice. And there it is, minus 2 a2 a3 b3, b2 b3. And so, right, top two rows, we ended up with this. Bottom two rows, we ended up with this. Okay. Turns out, right, if you look, this is the magnitude of vector A squared times the magnitude of vector B squared. All right. This is the dot product squared. Now, we got a lot better here. So we started with A cross B magnitude squared. Now we're down to magnitude A squared times magnitude B squared minus A dot B squared. But A dot B squared, that's the same as A magnitude A squared times magnitude B squared times cosine squared of theta. Theta is the angle between the two A, B vectors. But we can factor out magnitude A squared times magnitude B squared from both of those. We'll end up with magnitude A squared times magnitude B squared times 1 minus cosine squared. And then 1 minus cosine squared is a trig identity. We can replace that with sine squared. Then you do have to be careful, because when you take the square root, you have to make sure that sine is going to be positive when you have a sine of theta. So one way to ensure that is theta has to be between 0 and pi. All right, so that's how we got it. So we have magnitude of A cross B squared equals magnitude A squared times magnitude B squared times sine squared of theta. And as long as theta is between 0 and pi, sine of theta will be positive. So then we'll have a positive number, the magnitude A cross B equals magnitude A, which is positive, magnitude B, which is positive, times sine of theta, which will be positive. All right, so geometrically, what does this mean? So the magnitude of the cross product also has a nice geometric meaning. And so because we went through that horrible previous board in order to get this relationship, we can draw out what that means. So if I have vector A, and yeah, I'm going to make this one much longer. I have vector A, and I cross it with vector B, and there's my angle. I'm going to draw out a parallelogram, so okay, I think I got that pretty good. Okay. The area of this parallelogram is the height times the length. So if we want to figure out the height, well, there's the height. And so we can use the, let's see, so if we know what B is, right, this is the length here, is the magnitude of B. And I want to know what this height is. So if I have sine of theta equals, God, what is that, opposite over hypotenuse. Well, okay, that is currently this unknown sign that I want. It's the height over magnitude B. All right, so then I should have that magnitude B is equal to, magnitude B times sine theta is equal to the height of this parallelogram. And the area of the parallelogram is equal to the height times the length. Length. Oops, forgot my T. Okay, so the height, right, that is magnitude B sine of theta, and the height is magnitude A. But that's exactly the cross product, the magnitude of the cross product, excuse me. All right, so we've got these nice three rules about cross product now. So cross product of A cross B follows the right-hand rule. So if I cross A with B, the cross product vector is going to point out of the board in this instance. If I did B cross A, it would point into the board. So one consequence of that is A cross B is equal to negative B cross A. They point in opposite directions. All right. The follows the right-hand rule. And the magnitude of A cross B is equal to the area of parallelogram. I'll make it long. A, B. It's the area of that parallelogram. All right, so and you've got a nice handy-dandy way to compute the cross product now using that determinant of the 3x3 matrix. And so there you go.